This lesson is going to cover multiple grade levels. In 7th grade, we look at the angles within a triangle, we look at the angle sums within a triangle, and we incorporate it into different polygons. In 8th grade, we bring on the Common Core Standard 8.G.A.5, which is, again, taking on that 7th grade knowledge of 3 angles within a triangle, adding up to 180 degrees. But it also brings in the portion about the parallel lines and the transversal and an angle criterion for similarity of triangles. We also look at how if we were to take 3 copies of those angles and put them together, what that would create. That knowledge is then transferred up into our 10th grade geometry class, which is the high school standard G.Co.C10, and that's to be able to prove theorems about triangles. And in order to do that, we need to understand the measure of interior angles of a triangle and that adds up to 180 degrees. And also in geometry, we like to see how to find the interior angles of any given polygon. So this is a diagram that we show our 7th grade and pre-algebra students, and it's a triangle. And usually what we have students do is we have them take a triangle, they cut off the corners of the triangle, and then we ask them to piece them together, and it creates a puzzle that forms a straight line of 180 degrees. And that's how we prove that a triangle has 180 degrees within it. And when I do this, I like to take different types of triangles too, so students see that it's not just isosceles, it's not just equilateral, it is all types of triangles. And sometimes we redo this exact activity with 8th graders and geometry students, just so they see that conceptual understanding of why we have proven that triangles do have a total angle sum of 180 degrees. Of course, this could also be done with a protractor, but seeing it visually sometimes does help students understand it a little bit better. Okay, so we're going to take this to the 8th grade level as well as the geometry level. In the 8th grade, we learn about parallel lines and transversals. This is often taught to pre-algebra students as well, since the goal is that they will skip 8th grade math and take algebra in their 8th grade year. However, a parallel line with a transversal, there's our parallel set of lines, there's a transversal. And I'm going to go ahead and I'm going to draw another transversal going the other way. The reasoning behind this is I have now created a triangle in the center of those parallel lines. I'm now going to label some angles, so I've got 1, 2, and 3. Now, we're going to try to find some congruencies. If we remember back in prior lessons, we would remember that there are things called vertical angles, and vertical angles are congruent. That would mean that this angle and this angle, they are vertical, so they cross across that opposite area. The same thing as this one and this one are vertical, so 3 and 3 are vertical to each other, they are congruent, they are equal. And we could also go across and find that one is 2, it's also congruent to angle 2 on the inside of the triangle, and those are vertical. But something that we haven't talked about as much in the previous lessons is interior alternate angles, or alternate interior angles. So alternate means to go back and forth. Interior means inside. So our alternate interiors, they're created by that transversal with the parallel lines. The interior means it needs to stay inside of the parallel lines. So it can't be anything exterior of those parallel lines, only interior of them. So we're going to look at angle 3. Now, it can't be adjacent because it's congruent. We're looking for something that would be congruent. And angle 3 is not going to be congruent to this area over here. That's an obtuse versus a acute angle. So that's definitely not going to be our alternate interior. So while yes, we are alternating to the opposite side, we're staying inside, we actually need to alternate from the bottom to the top as well. So it's other side on the top, inside the parallel lines, That's going to be our congruent angle right there. So angle 3 and angle 3 are congruent, they are equal. Now we're going to look at angle 1. Angle 1 also has an alternate interior, so we're going to go to the other side of the line and go to the top. We're still inside those parallel lines, and we can see there is our congruent angle to our triangle angle 1. And again, you'll notice that angle 1, 2, and 3 form a straight line, creating that 180 degrees. Knowing this information and being able to apply it and explain it helps in geometry when you're doing proofs to do the triangle angle sum theorem and understand what that theorem means and how to utilize it to apply it to proofs. Okay, so we took it to a level where there was transversals and there were parallel lines, but now we're going to go back into the idea of the interior angle sum of a given polygon. And we know that one triangle has 180 degrees. So how many triangles can we make if we draw a line from vertex to vertex with no intersecting lines within the shape? So if I draw a line across this rectangle, I can see that there are two triangles. This one has 180 and this one has 180 degrees. So we're basically saying 180 times 2, which equals 360 degrees. Most students know this by 6th, 5th grade because they've learned that a right triangle is the corner of a rectangle and that there's 4 right angles in a rectangle, and so they know that. They know 4 times 90 is 360. But this also visualizes why is a triangle 180. So we've shown it with the paper, we've torn off the corners, we've shown it conceptually, but if you think about slicing a rectangle in half, you see that 2 triangles equals 1 rectangle. And this is applied to area formulas. It's applied to a lot of information in geometry. We're going to move on to pentagons though, because the rectangle is a known shape. We know that it's 360 degrees inside of it, but the pentagon is a 5-sided figure. And how can we apply what we know about triangles and the rectangle to the pentagon itself? And so what we're going to do is we're going to draw lines from vertex to vertex. So there's one vertex to vertex, there's another one. And what we end up doing is we can end up creating 3 triangles. So we can see that we have 3 triangles. Notice that none of my lines are intersecting inside of the actual pentagon. What I mean by that is we don't want to see lines drawn where I have a line here, and then I have a line here, and then I have a line here, and we can see all these spots where things are intersecting. That's creating more angles, and that would cause our calculation to be invalid. We want to make sure that we only keep those initial 5 interior angles. Even if we're splitting them with a line, we're not creating any new ones. And so we have our 3 triangles. We multiply that times 180 because we know each triangle has 180 degrees, and we find that the interior angle sum of a pentagon is 540 degrees. Now we're going to apply that same strategy to the hexagon. So as we add sides to polygons, it gets a little bit more difficult to figure out how we should draw these lines so that we don't have intersecting inside the center of the shape. And so if we draw vertex to vertex, we should end up, and yours might look a little bit different than mine, you should end up with 4 triangles. So each triangle has 180 degrees. That's going to be multiplied times 4 because we have 4 triangles. Okay? And we're going to get 720 degrees. And that's the total angle sum of any given hexagon. This one's even more difficult because now we have 8 sides, and it's hard to find which ways to go sometimes. So we're going to do the best we can. We've got 2 triangles so far, I've got a third triangle. Now if I go across, I'm going to have this big center square in the middle. So rather than do that, I'm going to go diagonal. And then I'm going to come back down. So I end up with 1, 2, 3, 4, 5, and 6 triangles. So 6 triangles. Each triangle has 180 degrees. So that's why I'm going to be able to multiply 6 times 180 to get my answer, which is 1,080 degrees. Okay, so now I'm going to go back a little bit into what we tend to use as an exploratory application of this information in hopes that students put together the patterns that they're seeing and possibly even write a formula to find the total angle sum of any given polygon. And in 7th grade we use this table format. Also, we'll bring it back in 10th grade just to reiterate the information or let the students explore it a little bit and see why things do work the way they do. Here we have a column that just says number of sides, so I'm going to quickly populate that. A rectangle has 4 sides, a pentagon has 5 sides, hexagon has 6 sides, and an octagon has 8 sides. Now we're going to go back to those number of triangles. So the rectangle had 2 triangles. The pentagon has 1, 2, 3 triangles. The hexagon has 1, 2, 3, and 4. And then, of course, our hardest one to draw, the octagon, we have 1, 2, 3, 4, 5, and 6. And this time I drew it a little bit differently, so it looks kind of like a shell. So looking at the information in the number of sides column versus the number of triangles column, what information do we see happening? So from number of sides to number of triangles, we see that we are 2 less. So then we look at the next one, 5 to 3, again we're 2 less. 6 becomes 4. Looks like a subtraction of 2 is happening. And so that's what we hope students get to, is that they notice that the number of sides minus 2 equals the number of triangles. And then taking it a step further, they realize that taking all of that information then needs to be multiplied times 180, gives us our total interior angle sum. So we're going to try applying that again. So starting with our rectangle, and we're going to look at what the formula might be for this. So remember we said sides minus 2 gave us the number of triangles. Well, the number of triangles we're multiplying times 180. And so there's our formula we're looking at. And with the rectangle, we have 4 sides. We're going to subtract 2 from it and multiply it times 180. This is going to equal 2 times 180, which does equal 360. And we know for a fact that that's the number of degrees within a given rectangle or a square. So the next shape we're going to take is the pentagon and try that as well. So the number of sides, we have 5 sides. So we're just plugging it into where sides goes. 5 sides minus 2 times 180. 5 minus 2 is 3. We multiply that times 180. And what we're going to end up with is 540 degrees. Then we're going to bring in the hexagon. Our hexagon has 6 sides. We substitute our number of sides with 6. Subtract 2. Multiply times 180. 6 minus 2 is 4 because we do our parentheses first. Multiply times 180, and this time we're going to get 720 degrees. Lastly, we bring in the octagon. The octagon has 8 sides on it. So we put 8 minus 2 times 180. 8 minus 2 is 6. And we're going to multiply that times 180. And our solution is 1080 degrees. So the actual geometric formula is just s minus 2 times 180. And that's the formula that we'll use for interior angle sum when trying to find it for any regular given polygon. That concludes this lesson. Please let me know if you have any questions. Thanks so much.